All right. Like usual, this lesson is brought to you by Yaaka Digital Network. It is free of charge for now, and we're offering very many classes. And for P1, P6, I mean to senior 6, not P6, obviously. From P1 to senior 6. And our offers, when it's not free, they're always here for the whole year to access teachers and our work online, notes, examination papers, and many other things. You pay 500,000 shillings to access Educare. The prices are here monthly, quarterly, half a year, and annually. Okay. So who can remind us on what we looked at the last time we were here? What did we look at before we go to today's lesson? Remind us what we looked at last time if you were here. Yes, Giovanni?
Last time we looked at bonding and the types of bonding.
Okay, that is correct. We looked at bonding, okay, and the types of bonding. That's good. Edgar, do you have another idea?
We looked at the bonding.
Bonding, that is correct. Yeah, we looked at bonding. We saw the different types of bonding, how these atoms get to interact with one another to form new compounds. Okay. Now, today we are going to continue with that, except we are looking at what happens after bonding. Okay. These atoms, how are they arranged in the structures they form after bonding? So that's why today we're looking at the structure of compounds or substances. So it's the next step after bonding. Okay, when these atoms bond together, they form various structures. We're going to expound on them to see the different types that exist. So different types of binds give rise to different types of structures. And this is illustrated here in this table. So when atoms bond with one another, they form various structures. Okay. An example, we have ionic or electrovalent bonding. Electrovalent bonding forms a structure that we call the giant ionic structure. Okay. And in covalent bonding, we see that we form simple molecular structures and giant molecular structures. These are the results of covalent bonding. Okay. Then in metallic bonding, we see that giant metallic structures are formed. Okay. So those are the structures that we form due to bonding. We're going to look at each structure and expound on it a little bit. I don't know if you guys can hear me well, but today's Zoom is a little bit sketchy. And it's not my network, unfortunately. All right. Let's start with the giant ionic structure. This one is the one that rises from electrovalent bonding or ionic bonding. This is a giant structure consisting of regular arrangement of a large number of oppositely charged ions, resulting into a three-dimensional crystal. Okay, so this results into the making of crystals. Each ion is surrounded by a number of oppositely charged ions, and they are held together by strong electrostatic forces of attraction. The number of ions surrounding a given oppositely charged ion is known as the coordination number. Examples of this structure, we have sodium chloride, and you can bear witness that sodium chloride, which is the table salt you have at home, is crystal-like. It's made up of crystals. This shows that it consists of giant ionic structure. Magnesium chloride is another example, and there's so many other examples. Now, the structure of sodium chloride looks like this. This is the giant ionic structure. We have the positively charged ions, okay, the ones in dark here. Those are the sodium ions, as you can see. They are surrounded by negatively charged ions, which are in this case chloride ions. These other ones, okay. Now, for example, each positively charged ion, you see that it is surrounded by 4 negatively charged ions. Okay, if the structure is complete, just like this. Okay. So this middle one is surrounded by these, the ones that I'm pointing towards the sodium ion. Okay. So this sodium ion right here is surrounded by these 4 negatively charged chloride ions. And that's how it works. As a result, it forms this giant ionic structure, which is a 3D structure, and it forms in the form of crystals. So in the environment. So that is the giant ionic structure. Okay. Another way we can explain this in a more visible way is to say that each ion is surrounded by 6 chloride ions, and each chloride ion is also surrounded by 6 sodium ions. The coordination number there is 6 to 6. Actually, not 4 to 4, but 6 to 6. There is the middle one that I missed. Okay. So here it is in a 3D shape. In a 3D shape, this is how it will look like. Remember to ask questions if you don't understand. So here they are named very well, that you can see the chloride one and the sodium ions. Yes, Nicholas?
Teacher, I have not understood the other table.
The what? The table?
Yes.
I don't think it was a table. You mean this? Nicholas, you mean this?
Before that.
That was the beginning. It was just the introduction of the structures. This. We were saying
Okay,
the type of bonding, and the structure that is formed. We have the ionic bond, it forms a giant ionic structure. The covalent bond forms 2 types of structures, a simple molecular structure and a giant molecular structure. The metallic bond forms a giant metallic structure. These types of bonding we looked at last time we were here. So I'll implore you to go find those notes in the group and then go through them. Today we are concentrating on the structures of each type of bond. Okay. So yeah, that is the giant ionic structure. Each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. Okay, if the structure is complete, this is just one sort of it is like a one sort of crystal that is formed from when you have crystals combined, you see that this how the six atoms come about, the six ions come about in surrounding each other. Okay. I have some nice videos on the website that show the 3D combination of the different crystals. When you subscribe, you'll be able to access them. Okay. So let's look at the properties of these ionic compound or ionic structures. Yes, Hamira?
Teacher, I didn't understand when you were explaining the giant ionic structures. When you said each sodium is surrounded by 6 chloride. I was confused.
Okay, let's look at this one, which is not in it is not in a 3D shape. So, for example, it is very, very hard to see here, but here is the deal. You see the sodium ion is surrounded by this chloride ion. Okay, let me put all the chloride ions that surround this, the one in red, the sodium ion, in yellow. This one too. So those are 3. There's another one here on the side here. Okay, those are 4. There's another one in the middle here. Okay, those are 5. Now, so those are 4, and the 5th one is right here. Okay, now if another crystal comes along and it is up here, there's going to be another chloride ion connected here. Okay, so that will make a total of 6. All right, right here we can only see 5 because we don't have another crystal on top of this crystal. But if we add one, you see it connected, okay, at the top here. That's what I meant by each sodium ion is surrounded by 6 chloride atoms, chloride ions. Okay, so that's the explanation. Does that make a little bit or more sense for you, Amir?
Yes, teacher, it is.
Okay, good. All right. So here are the properties. The properties we have, they are solids with a regular shape. This is because of the strong electrostatic forces of attraction, keeping the ions closely packed. So every compound that forms a giant ionic structure is always solid. Okay, they're solid at room temperature because of the forces of attraction, the electrostatic forces of attraction that keep the ions closely packed. They have a high melting point. This is due to the strong electrostatic forces of attraction between the oppositely charged ions. Okay, and then they do not conduct electricity in solid states, but do conduct in molten states or solution form. This is because in solid states, the ions are localized and the electrons are not mobile. But in molten form, the ions and the electrons are free to move because they become delocalized and thus conduct electricity. So in other words, the reason why they don't conduct electricity is because the ions, while in solid state, they cannot move. They are strongly packed together and they are held by strong electrostatic forces. Okay, so they can't move in solid state. But once you melt them, then the ions are free to move. they become delocalized, and hence they can conduct electricity. Any questions about that? Okay. If you feel like asking a question, please raise your hand. The other property is that they have a high density as the ions are closely packed. Again, that close packing there it leads to a couple of properties. Ionic compounds are soluble in water and other polar solvents, but they are insoluble in organic solvents like benzene. Ionic compounds dissolve in polar solvents like water as the ions are attracted by the polar molecule. So we see that they're very soluble in water because of the fact that they are made up of ions. So they can ionize easily in solvents like water. Okay, the moment the solvent is polar, the solvent can make ions, then can dissolve these type of compounds, these ionic compounds. But we see that they cannot dissolve in organic compounds or organic solvents because these organic solvents are not polar. By the meaning of polar is the ability to form ions. Okay. So solvents like benzene will not be able to dissolve these ionic compounds. So that's the explanation of their solubility. If you have a question, you ask. Yes, Nicholas.
I have not understood that property 5.
Okay, what don't you understand on property 5? What is confusing you?
I'm not getting it well. The whole
Is it the
statement.
Oh.
What?
Okay. See here we're saying these ionic compounds are soluble in water and other polar solvents. What this means is that these polar solvents, even water is a polar solvent, okay? Polar solvents are able to form ions. They're able to form ions so that they can dissolve ionic compounds. Okay, that's what we're saying. And we're saying they are insoluble in organic solvents because organic solvents are not polar. Okay, organic solvents are not polar, so ionic compounds cannot dissolve in them. You see, when a polar solvent forms ions, okay, these ions attract the ions of the solute. So when these ions attract each other, then they mix up so that the dissolvement takes place, or the ability to dissolve is available, all right? But if we have a solvent that cannot make these ions, if it is not polar, like the benzene is not polar, then there's no dissolving of the solute of this ionic compound. It's not going to dissolve because there is no ions to attract it to the solvent. But if a solvent has ions to attract the ionic compound, then it will dissolve. So that's the simple explanation. Okay. All right. So a polar compound is a covalent compound in which charge separation exists, okay, between atoms. This is due to the difference in electronegativity between the atoms. This charge separation here is the ionization that we're talking about, okay? The charges separate so that each charge can attract the opposite charge from the solvent, from the solute, actually not the solvent, from the solute, which is the ionic compound, right? And then electronegativity is the tendency of an atom to attract bonding electrons, towards itself. Okay. Electropositivity is the tendency of an atom to push away bonding electrons from itself. So now here, this term electronegativity is not very, very common in our O-level chemistry, but essentially what it means, electronegativity, when you have electrons in an atom, that atom will always want to pull those electrons towards itself. Okay. When you look at an atom, we have inside, we have a nucleus, and then we have the shells or orbitals where electrons are formed. Okay. Now, the electrons in the orbitals are always attracted towards the nucleus, since the nucleus is positive, and we know unlike charges will attract each other. So the electrons on the orbitals are always being pulled towards the nucleus. Okay, that is electronegativity right there, pulling electrons towards itself, an atom pulling electrons towards itself. We call that electronegativity. Now, the opposite of this is electropositivity. Okay, the bonding electrons are pushed away, meaning this atom is ready to give them away. Okay, let's say it's a different atom, and it is ready to push away the bonding electrons, just like that. Okay. Sometimes this is because of the shielding effect that is available in the orbitals around here. Okay. The nucleus is not so much positive to attract these bonding electrons. Instead, it pushes them away due to the many electrons that are in the other orbitals. So that's the easiest way I can explain this electropositivity and electronegativity. Okay. If you find time, you can read more about it and see exactly what we mean. There's some nice videos that explain it way better than me. But essentially, that's what it is. Any questions on this? Okay. An example we have is a water molecule. In a water molecule, oxygen is more electronegative and attracts the bonding electrons towards itself, giving it a partial negative charge. Hydrogen attains a partial positive charge. So we see that in the oxygen atom, there is a lot of nuclear energy, meaning, or nuclear attraction, meaning the electrons, the nucleus of oxygen is capable of attracting its bonding electrons towards the nucleus. So that sort of thing. The bonding electrons are the ones found in the outermost shell. So this makes it more electronegative, and it leaves a negative partial charge onto the oxygen atom. What that results into is making the hydrogen attains a more positive charge in the water molecule. So we have that type of thing. Okay, the oxygen is negative, the hydrogen is positive. This is polarity now. Okay, this is polarity. Maybe we had something like this. Let me see. Okay. This is the oxygen atom. Okay, we'll have a partial negative charge here and a partial positive charge. This is what we call the polarity. separation of these charges or atoms. And this will attract the ions of the ionic compound. Let's say if it is sodium, if it is sodium chloride, okay. If it is sodium chloride, we have the chloride one that will be negative, and then the sodium that will be positive. So these ones will attract these, okay, and that's how dissolving takes place. So we said a polar compound is a covalent compound that in which charge separation exists. Someone who is asking about polarity in the comments. So when we have a covalent compound where the charge separation exists, we say that compound is polar. That's what I've been explaining. So charge separation in a covalent compound is polarity. Okay. So the other example here in the structure of water is, as we can see, we have positive charges on hydrogen. Okay. Positive charges on hydrogen. We have positive charges on hydrogen and a negative charge on oxygen. These are partial charges. They are not permanent. They are partial charges just to help in dissolving. Yes, Christian, you're right. Yeah, partial charges that are found in a covalent compound. The separation of these charges is what we call being polar. So now this water molecule is very, very ready to receive an ionic compound due to the formation of these partial charges. That's what it means. Okay, very good. As if you have questions, you can always ask. If you want, you can type them in the chat box or you can raise your hand. Simple molecular structures. Let's look at simple molecular structures. These are made by covalent bonding. Okay. The structure consists of simple independent molecules joined together by weak intermolecular forces of attraction. Okay. Someone is writing on my screen seriously. All right. E.g., we have the weak intermolecular forces. An example we have is the van der Waals forces of attraction. Those are weak intermolecular forces. The atoms in the molecule are held together by strong covalent bond. Compounds with this structure exist as gases, liquids, or solids with low melting points. Examples include iodine, carbon dioxide, ammonia, water, etc. So here we're just looking at those compounds with a simple molecular structure. Okay, we have said that they are held together by weak van der Waals forces of attraction, but the atoms in there are held together by strong covalent bonding. That's exactly what we mean there for us to have a better picture. So, for example, here we have iodine, structure of iodine. We have here the strong covalent bond holding iodine atoms together. Iodine is diatomic, so it's made up of two atoms, and the two atoms are held together by a very strong covalent bonds. Okay. But each of these, okay, is connected to another molecule, okay? Each molecule is connected to another by weak van der Waals forces, okay? So the molecules are held together by the weak van der Waals forces, which we see right here, right? These are the weak van der Waals forces. They are holding the molecules together. So this is the simple molecular structure of iodine, all right? The atoms, very strong covalent bond holds them together, and then the molecules are held together by weak van der Waals forces. Any questions on that? Okay. So that is the simple molecular structure of iodine. Another one here is an illustration of weak hydrogen bond in water, right? Here is another simple molecular structure. Again, we see the atoms in water are held together by strong covalent bonds. Okay, the atoms held together by strong covalent bonds. But the molecules, this is the molecule now. The entire molecule is connected to another molecule by weak hydrogen bonds. So this is what we talk about when we say that there is hydrogen bonding in water. It's between the molecules, not between the atoms, but the molecules. That's the difference. Between the atoms, we have strong covalent bonding. But between the molecules, very, very weak hydrogen bonding. So this is the hydrogen bonding. Okay, you can see each atom, each molecule is connected to another by these bonds. That's what we mean. Any questions so far on that one? Simple molecular structure. Okay, so that's the simple molecular structure of water. For it, the molecules are connected with weak hydrogen bonds. We saw in iodine, it's the weak van der Waals forces of attraction. Here are the properties of a simple molecular structure. They have low melting and boiling points because the molecules are held together by weak intermolecular forces of attraction. They are non-conductors of electricity because they do not have mobile electrons or ions. Most of them are gases and liquids. Very few are solids. Okay. They have low densities as the molecules are not closely packed. They dissolve in organic solvents. Now, when we find a compound that has a simple molecular structure but is capable of being polar, it has polarity, then this factor here, number 2, ceases to be correct if it is polar. If it is polar, it means there is separation of charge, so charges, ions can move around. This is why we see that water is capable of this conduction here. So don't pour water in electricity and think that it's not going to shock you just because it has a simple molecular structure. Water is polar, so it has mobile ions. It's able to separate its ions so that they can conduct. Let's look at the giant atomic or molecular structure. So these ones are the giant atomic or molecular structures. Please, if you have a question, remember to ask. Feel free. Okay. Compounds with such structures consist of molecules or atoms linked together by strong covalent bonds, resulting into a giant. Yes, please. Someone has a question, but your network is very, very low. Type the
Excuse
question
me,
in the
teacher.
chat box. Yes. We can't hear you. Your network is very bad.
I want to know the meaning of polar.
The meaning of what? If I'm hearing you well, you're saying polar, right? Are you saying polar, the meaning of polar? I've explained that a couple of times. But also Christine put a very simple explanation in the chat box.
Meaning of polar.
Okay, the meaning of polar. I've explained that a couple of times. I think you joined late. But check in the chat box. Christine tried to explain it to someone. Try to explain it to Hope, okay? So check in the chat box. I explained it, and also Christine tried to type it in the chat box for Hope. So check in there as we continue. So covalent bonds result into structures like that in graphite, diamond, respectively. We can see the details here. Let me see. We have examples of these giant molecular structures with this picture here. Okay, we can see individual molecules that are connected up here to form the strong. Please mute your sound. I don't know, someone forgot their sound on. Mute your audio. Hope mute your audio and Patrick. The name says Patrick, but someone who is speaking is the lady. So up here we see the individual molecules that make up the giant structure, the giant molecular structure. Okay. So for example, the molecule that forms in diamond is right here. Okay. This is the one that is connected to form this giant molecular structure. So in diamond, this is a tetrahedral structure. Okay. As you can see, there are 4 sides to it. Each carbon atom is connected to 4 other carbons. Another giant molecular structure we see is silicon dioxide. Silicon dioxide. As you can see also here in silicon dioxide, this is the molecule, the individual molecule. This individual molecule is connected to form this type of giant molecular structure. Okay. That's what it means. Also, silicon carbide. Silicon is very good at forming these giant structures. So silicon carbide, you can see the individual molecule is this, and then it is interconnected. The molecules are bonded together to form this giant molecular structure. Remember, it is covalent bonding in there. Then for graphite, it forms sheets like this. Hexahedral. There is a hexahedral structure, and then it forms sheets that are connected by weak van der Waals forces. So that's why graphite is a little bit soft compared to all the rest of this side, because of the sheets connected together by these weak van der Waals forces. Okay, but the sheets are made up of covalent bonding connections. All right. So that is the giant molecular structure. This is how it is formed. Any questions? Someone forgot their audio on, please, if you can hear me. Yes, Edgar.
I have not understood that silicon dioxide.
Silicon dioxide?
Yeah, the structure I have not understood.
It's the same with every other structure that you're seeing on this picture, okay? The individual molecule is right here, okay? The we have silicon being bonded to 4 other oxygen atoms. All right. Then this is interconnected here with strong covalent bonding to form this giant molecular structure. Okay, so those individual molecules you see up here, are the ones that form the giant molecular structure of silicon dioxide. It's just the interconnection. Okay. As you can see, if this is the silicon atom, it's going to be bonded to by other 4 oxygen atoms. Okay, that's how we can explain that. Any other questions? Okay, we can continue. The properties of giant molecular structures are here. They have a high melting and boiling points because of the great energy needed to break the bonds. They do not conduct electricity except graphite, which has delocalized electrons. They are insoluble in water. Giant metallic structures consist of very many metal ions surrounded by a sea of ground electrons. These ones we looked at last time, the giant metallic structure. So this one is easy to explain if you looked at the notes that we had last time for the giant metallic structures. We saw very nice explanations and pictures of the giant metallic structure last time. But for those who are not around, here is another explanation. So for the giant metallic structures, we have a metal lattice. Okay, a metal lattice. This metal lattice consists of positive ions. Okay, positive ions, the green ones, surrounded by a sea of electrons. Okay, these electrons are free to move around in the metal lattice. These ones here, you see the black ones. They're free to move around in the metal lattice. So the positive ions form the crystal lattice, while the delocalized electrons move freely throughout the lattice, gluing the whole lattice together. So this is why metals are able to conduct heat and electricity. It's because of these electrons that are free to move around. They are delocalized. Okay, delocalized means being free to move. If you're localized, you are in the same place. For example, right now Uganda is localized. We are in lockdown, so we cannot move to freely to where we would want to move. If that lockdown is opened, then you'll be delocalized. You can move everywhere you want. Exactly, it's the same thing happening here in the metal lattice. The positive ions are localized, but the electrons are delocalized. They are free to move around in the metal lattice. And this also facilitates the formation of the lattice, meaning the positive ions are held together. Okay, the attraction of electrons help to hold together the metal lattice. So that's the explanation of the giant metallic structure. This is why metals, like I've said, are capable of conducting heat and electricity. Any questions on that? Okay, the properties, these are solids and with very high melting and boiling points, except for mercury, which is a liquid. They conduct electricity in both liquid and solid states due to the presence of mobile electrons, like we have said. And that's it. That's what we had for today. Please, I would send out these notes. Make sure you go through them. Go through them, and I'll send you an exercise. This exercise will also contain questions about what we had last week. So make sure you go through it. What is the meaning of oxidizing? Someone, Elisha, was asking about oxidizing. Okay, oxidizing is just addition. Actually, it's addition or removal. It's actually removal of electrons. You get oxidized when you add electrons or remove electrons, one of the two. Let's talk about salts too. Yeah, I'll talk about salts later. Don't worry about it. We'll talk about salts. Okay, thank you for attending. Make sure you are active in the group. I'll send out the notes. Oxidization does not necessarily mean combining with oxygen. Oxidation can mean various things. Okay, being oxidized, when you gain electrons, you become oxidized. Okay, could mean cause undergo reaction with electrons are lost. Another species. Okay, yeah, that's true. So there's a very, very good connection between reduction and oxidation. So for example, in a redox reaction, we have gain and loss of electrons. Okay, that's a redox reaction. It is a reaction where we have gain and loss of electrons from one species to another. Right? But when you lose electrons, you become oxidized. You become more positive, right? When you gain electrons, that's reduction. You become reduced. So yes, Kristen, that is a better explanation. It's not necessarily a reaction with oxygen, NED. Okay. Sometimes it has nothing to do with oxygen. All right, good job. Thank you for attending. Let us wait for these notes. We'll go through them, and I'll send you the activity also in the group. Good job. Someone is asking, what about removal of hydrogen ions? Okay, that's another explanation to mean oxidation, especially in organic molecules. You see that when you remove hydrogen ions, you become oxidized. So good. All right, good questions today. Let's look at that again next week. Thank you for attending. See you soon. Well done.
Thank you, sir.
Mhm.
Thank